Hey, everybody. I hope your day is going well. Sorry I'm not here in person to teach you today. But what I'm going to do instead is teach you the section of Note Packet 9 I plan to teach in class through this super fun YouTube video. So if you don't already have it out, please grab out your Note Packet number 9, and we should be on the next available section, which is Solutions and Saturation, which is, saturation and solutions, which is on page 5. So take a moment, if you haven't already, grab out Note Packet number 9 and open it to page 5. We should be on this page for saturation and solutions. Okay, so I'm going to go ahead and go through some notes on saturation, which is like you can have a unsaturated, supersaturated, or just plain old saturated solution. And then I'm also going to teach you about solubility curves, which are graphs of like how much stuff you can dissolve in a set amount of solvent at a particular temperature. And then for the second half of the block, you'll work through a gizmo where you go ahead and create a solubility curve. Okay, so I'm going to go ahead and share my screen. And again, we are working on out of Note Packet 9, page 5. All right, there we go. Oops, not that tab. All right, here we go. All right, so saturation and solubility curves. All right, so basically what we're going to learn today is about saturation. And basically what saturation is it's the ratio of solute to solvent. So like how much solute do you have per this amount of solvent? The more solute you have dissolved in the solvent, the more saturated the solution is. So there's 3 overall classifications of saturation in terms of solutions. There are saturated solutions, unsaturated solutions, and supersaturated solutions. Okay, so a saturated solution is a solution that has like the perfect amount of solute dissolved in it. These are solutions where you cannot dissolve any more solute in them under the given conditions. So they're perfectly saturated with solute. So really why this is you have dissolved enough solute in your solvent, like your water, that all the available spaces between your solvent molecules are perfectly filled with solute. So if my solute was salt and I wanted to make a saturated solution of salt and water, I would have to dissolve enough salt so that every single available space between water molecules was filled by a salt molecule. And if I filled up all those available spaces, I would have a saturated solution. I could not dissolve even one more grain of salt in the solution because all the room between solvent molecules is taken up. An unsaturated solution is pretty much exactly what it sounds like. This is a solution that you can still dissolve more solute in. These are solutions that you are able to dissolve more solute in under the given conditions. So an example might be taking a teaspoon of salt and dissolving it in a 5-gallon water bucket. If not all the available space between the solvent molecules is filled, so there's still some space left in the solution, you can still dissolve more solute in it. That is an unsaturated solution. A supersaturated solution. These are kind of weird because these are solutions that you have somehow, there's really 2 ways you can do this. You have somehow dissolved more solute than should be able to fit between your solvent molecules. So these are supersaturated solutions. They contain more solute dissolved in the solvent than can usually be dissolved under the given conditions. So probably the biggest way to do this, if you wanted to do it at home, say, oh, I didn't highlight this stuff, I'm sorry, is to use heat. So basically what you can do is make a saturated solution at a higher temperature. So like heat up your solvent to a higher temperature, like boil some water and dissolve as much salt as you can in that boiling water, saturate it. And then allow the solution to slowly cool to a lower temperature. And if you allow the solution to slowly cool to a lower temperature and you don't disturb it, what you will do is create a supersaturated solution. Now, this solution is going to be super duper unstable. And even the smallest disturbance is going to cause the extra dissolved solute to precipitate or fall out of the solution. So basically what happens here is if you heat your solution up, you create more space between your solvent molecules. The water molecules, say, they spread apart. So you can dissolve more stuff in a hot solution, hot water, than you can in cool water. So basically you dissolve as much possible salt in, say, your water as you can at a high temperature. You saturate it. And then if you allow it to cool slowly undisturbed, usually what you can do, if you really don't disturb it, is allow those water molecules to come back closer together. And due to electrostatic attractions between the solute and the solvent, like the salt and water molecules, that extra salt will stay dissolved in the solution. Now, even the slightest disturbance will cause that extra solute to precipitate or fall out of the solution. And that's what this GIF over here on the right is showing. This is a supersaturated solution of sodium acetate. It was created at a high temperature, and then it was allowed to cool slowly to room temperature. What you see is in the middle is the scientist introducing one just more crystal of sodium acetate. It's like a salt into this supersaturated solution. And by simply like inserting that black rod you see with the one additional crystal into the solution, all that extra stuff that's been dissolved in it, you can see precipitating fall out. And it does so in a pretty manner, right? Kind of makes like a star as it falls out. All right, so supersaturated solutions, they contain more dissolved solute that will normally fit between your solvent molecules. One way to create them is through heating. Start by creating a saturated solution at a higher temperature. Allow it to cool slowly to a lower temperature. If you leave it undisturbed, you will keep that extra stuff dissolved in it, but they're very, very, very unstable. Okay, so there's your three saturations of solutions: saturated, unsaturated, and supersaturated. Now we're going to shift gears a bit, and we'll come back to saturation in a minute, and we're going to talk about solubility curves. So what you see up on the screen is table G in your reference table. It gives solubility curves for different substances dissolved in specifically 100 grams of water at a certain temperature in degrees Celsius. So any point on any of these curves here represents the amount of that solute, so like the amount of NaNO3 that can dissolve in exactly 100 grams of water at a particular temperature and create a saturated solution with it. So the key is when you're working with table G is you have to remember this is how much of these substances, their mass in grams, that's the Y, that can dissolve in exactly 100 grams of water at a particular temperature. So sometimes when you're asked questions from table G, you can just straight up read the graph. Other times you have to think about it a little bit because that whole point that I keep trying to reiterate, the 100 grams of water, that's the amount of solvent you're using, is important. So the first let's practice says how many grams of NaNO3 can dissolve in 100 grams of water at 10 degrees Celsius. So as long as the amount of water given in the problem, the 100 grams, matches the 100 grams on table G, you can literally interpret the table as is. I would find 10 degrees Celsius on the x-axis. I would read up until I hit the curve for NaNO3, read over to the Y, and that would tell me about 80 grams of NaNO3 will dissolve in exactly 100 grams of water at 10 degrees C. Sometimes you'll get questions where they'll say the same thing, how many grams of NaNO3 can dissolve in 200 grams of water at, say, 10 degrees Celsius. Well, if I had twice as much water, I could dissolve twice as much solute. So if 80 grams can dissolve in 100 grams of water at 10 degrees Celsius, 80 times 2, or 160 grams, should be able to dissolve in 200 grams of water at the same temperature. If I use twice as much water, I should be able to dissolve twice as much solute as at that temperature. Same thing, if I wanted to know how much NaNO3 could dissolve in 300 grams of water at that same 10 degrees Celsius, I would have 3 times as much water, so I should be able to dissolve 3 times as much solute at that temperature. So in this case, the 80 grams times 3, since we're using 3 times as much water, you could dissolve about 240 grams of sodium nitrate at 10 degrees Celsius in 300 grams of water. Okay, so that can be one tricky thing. They can ask you to go the other way. They can give you the amount of solute and ask you what temperature you could dissolve that at, all of that solute at. So what temperature should 100 grams of water be in order to dissolve 20 grams of KClO3? Well, make sure it matches the 100 grams of water given in the problem, matches the 100 grams of water that each of these solutes is dissolved in on table G. I want to know the temperature this time the water has to be to dissolve 20 grams of KClO3. So find the 20 grams on the y-axis, read over until you hit the KClO3 mark. Oops, I went too far, it's right here, sorry. And then read down. I think it's about 50 degrees C. I actually don't think that was right on the point. It might have actually been, it looks like maybe a hair above it. So there's usually some flexibility. You said 52 degrees C, that's fine. But it's just going the other way. They gave you the mass of the solute and they want to know at what temperature it would dissolve. All right, the last one, and then we have one more thing to do quick after this before we try the gizmo, is something like this. They want to know how many grams of a substance will precipitate or fall out of the solution when you cool it down. So this says if the temperature of a saturated solution of KNO3 containing 100 grams of water, so that matches the table G, is changed from 60 to 30 degrees Celsius, how many grams of KNO3 will precipitate, which means fall out of solution. So we're saying we have this KNO3 solution, and it has 100 grams of water, so it matches table G. It's made with 100 grams of water, and we're cooling that saturated solution down from 60 to 30 degrees. They want to know how much stuff will fall out as that solution is cooled. So you need to figure out how much solute will dissolve in a saturated solution of the substance at 60 degrees versus how much will dissolve in a saturated solution of this substance at 30 degrees. So if you go to 60 degrees on the x-axis and you read up till you hit the KNO3 curve, all the way up here, it looks like about 105 grams of KNO3 will dissolve at 60. And then we're cooling it down to 30 degrees Celsius. So you would read up until you hit the KNO3 curve again. It looks like about 48 grams can dissolve at 30 degrees Celsius. So taking the difference between those two should give us about how much would precipitate or fall out of solution. So in this case, it should be about 57 grams. Now, I approximated the mass that would dissolve at both of those temperatures, so you might get some variation there. But generally, figure out how much solute will dissolve at each temperature, and the difference between them as the solution is cooled is how much solute will precipitate or fall out of solution. All right, so the last thing we're going to talk about today is how you can use table G to determine if a certain solution is saturated, supersaturated, or unsaturated. So it's all relative to where the coordinates you're given, the temperature of the solution versus the dissolved mass of solute. It's all about how those coordinates relate to the curve itself. If the coordinates, the point that you plot, falls right on the curve, the solution is saturated. If the point you plot falls under the curve that you were looking at, if it's beneath it or under it, the solution is unsaturated. And if the point falls above the curve, the solution would be supersaturated because it contains more dissolved solute than should fit at a given temperature. So on the curve is saturated, under it is unsaturated, and above it is supersaturated, which is exactly what this says here. All right, so one more time. If the solution is saturated, point falls directly on the curve. If the solution is unsaturated, it should be able to dissolve more solute at that temperature. The point will fall under the curve. And if the solution is supersaturated, it has more solute dissolved at a given temperature than should be able to dissolve. The point will fall above the curve, meaning the solution is supersaturated. Okay, so to wrap up today, basically what we're going to do is we're going to look at table G again. We're going to plot the points we're given for a given solution, the amount of solute that is being dissolved at a certain temperature, and then relative to the curve for that substance, we should be able to figure out what type of solution we are talking about, saturated, unsaturated, or supersaturated. Okay, so the first one says if 80 grams of NaO3 are dissolved in 100 grams of water, right, and that's what table G is written for, at 10 degrees Celsius, is the solution saturated, unsaturated, or supersaturated? So let's plot the point. We are plotting 80, 10. So 10 is the temperature, 10 degrees Celsius. The mass of solute we're dissolving at that temperature is 80 grams. So the point is boom right there, which is directly on the curve for the substance given in the problem, NaNO3. So the point was on the curve, it was right on it, which means these are the conditions of a saturated solution. So dissolving 80 grams of NaO3 at 10 degrees Celsius in 100 grams of water will produce a perfectly saturated solution. All the available space between water molecules is perfectly filled with NaNO3 molecules. All right, let's do one more, and then you're going to work on the lab. This says if 100 grams of KNO3 are dissolved in 100 grams of water, which again is what matches table G, at 60 degrees Celsius, same question, is the solution saturated, unsaturated, or supersaturated? So let's plot the point 60 degrees C, 100 grams, so 60, 100. So we'll go up from 60 until we hit the 100 mark on the y-axis, the y scale. So that point is under the KNO3 curve. So that point is under the curve. A saturated solution looks like it should be able to dissolve about 105 grams, and we only are using 100 grams. Since the point is under the curve, This is an unsaturated solution. Okay, there you go. The basics. What makes a solution saturated, unsaturated, or supersaturated? How to read and interpret table G. And then how to also read and interpret table G to determine the overall saturation of a solution. So what I would like you to do now is, if you go to Google Classroom, you're going to work on lab number 25, which is the solubility and temperature gizmo. So you're actually going to use a gizmo to create your own solubility curve for a substance, and then you'll look at your curve and compare it to the actual curve for the substance on table G and see how good your curve is. All right, make sure you read the directions in the lab carefully, because it's going to tell you like what to look for and how you know if the solution you're creating is saturated. And of course, if you have any questions, either email me or save them for the next time I see you, which will be tomorrow. All right, everybody, have a good rest of your day, and I'll see you later. Bye.